Astronomie am Kepler.
Herzlich willkommen zur 25. Folge von Astronomie am Kepler, dem Astro-Podcast des BAG Kepler Graz.
Wir geben euch hier wieder einige Einblicke in den Astronomieunterricht an unserer Schule.
Mein Name ist Norbert Steinkellner und mein Team besteht wie immer aus den Schülerinnen und Schülern des Mehrschulenkurses Graz. Und heute machen wir wieder einmal einen Blick zurück zum Kepler-Teleskoptreffen, das wir vom 2. bis 5. Mai dieses Jahres eigentlich schon veranstaltet haben. Da sind noch ein paar Dinge offen, tolle Vorträge, über die wir überhaupt noch nicht geredet haben. Und ganz besonders freut es mich, dass es heute um einen Vortrag von einem Absolventen von uns gehen wird. Nämlich der Desmond Grossmann, der macht gerade sein Doktoratsstudium in Teneriffa. Der hat von der Uni Graz auf die Universität Teneriffa gewechselt. Warum Teneriffa? Weil dort die Instrumente stehen, die er braucht, nämlich die Großteleskope, mit denen er seine Beobachtungen und seine Messungen macht. Und was ihn interessiert, wozu er arbeitet, das sind Schwingungen der Sterne. Schwingungen, das kennen wir vor allem vom Schall. Schall sind Schwingungen. Wir hören schnelle Schwingungen als hohe Töne. Wir hören langsamere Schwingungen als tiefe Töne. Und heute geht es mal darum, wie wir Sternen zuhören können. Also, let's listen to the stars. Hören wir einmal, was uns die Sterne so zu sagen haben. Und zum Einstieg habe ich jetzt einmal ein Bild auf den Beamer geworfen, das ein bisschen schematisch zeigt, wie man sich so Schwingungen von einem Stern vorstellen kann. Hier ist also das Bild der Sonne, einfach also mal so gelb eingefärbt, und ihr seht da im Wechsel so rote Flecken und blaue Flecken. Und ich bin gespannt, ob wer eine Idee dazu hat, was es mit diesen roten und blauen Flecken auf sich haben könnte.
Also Rot hat eine kleinere Frequenz und hat dadurch weniger Energie, und die blauen Strahlen haben eine höhere Frequenz und dadurch mehr Energie.
Da haben wir also Bereiche auf diesem Stern, wo das Licht eine höhere Frequenz hat, und daneben haben wir wieder Bereiche, wo das Licht eine kleinere Frequenz hat. Okay, was muss denn das Licht tun, damit wir eine kürzere Frequenz sehen?
Ja, die Bereiche, die wir blau sehen, die bewegen sich auf uns zu, sozusagen.
Und die roten dann?
Von uns weg.
Und diese Bereiche, die liegen eigentlich so, wie man am Bild sieht, so ganz nebeneinander. Das bedeutet, eigentlich wobbelt der Stern, und zwar wobbelt der so ganz unterschiedlich. So, der verschiedene Bereiche von dem Stern zittern verschieden. Wir haben also solche, man nennt das stehende Wellen. So stehende Wellen, die durch den ganzen Stern durchgehen, und dadurch fliegen einige dieser leuchtenden Gase kurzzeitig immer zu uns her. Das ist dann blau verschobenes Licht, was wir kriegen, und die anderen gehen kurzzeitig von uns weg, und da haben wir dann rot verschobenes Licht, das wir von diesen Bereichen kriegen. Also eigentlich könnte man irgendwie sagen, so ein Stern, der aus Gasen besteht, verhält sich eigentlich gleich wie eine große Glocke, die man anschlägt. Na, bei der Glocke sind es natürlich keine Lichtwellen, die sich da fortpflanzen, sondern bei der Glocke sind es eben Schallwellen. Und wenn man diese Schallwellen auf der Glocke analysiert, wie schwingt denn die genauer, dann bekommt man solche bestimmten Muster heraus. Also nicht jeder Fleck auf der Glocke schwingt gleich, sondern da gibt es solche Schwingungsbäuche, wo die Glocke stärker schwingt, und es gibt so Schwingungsknoten oder Schwingungslinienbereiche, wo es gar nicht schwingt, wo quasi wo die Glocke stehen bleibt. Man kennt es von der Gitarre. Die Gitarristen unter euch, Gitarristen, ich demonstriere das einmal an meiner Versuchsgitarre aus dem Physikkämmerchen, die habe ich noch gelernt als Kind. Also wenn man seine Saite anschlägt, hört man einen bestimmten Ton, ja, je nachdem, wo ich meine Saite habe. Aber der Ton, den wir hören, ist nur ein Teil aller Töne. Es gibt also verschiedene Schwingungsmoden. Die Saite schwingt zum Beispiel so, dass so genau in der Mitte von der Saite so ein Bauch ist, der auf und ab schwingt. Das ist der Grundton, den wir eigentlich hören. So, und wenn ich jetzt diesen Grundton genau abdämpfe, das heißt genau in der Mitte der Saite, und die ist am 12. Bund, wenn ich genau an der Mitte der Seite abdämpfe, dann den Finger drauflege, dann dämpfe ich genau diese eine Grundschwingung ab und statt dem Ton kommt dann dieser. Der Ton ist genau eine Oktave höher. Das heißt, die Schwingung ist da quasi so bei einem Viertel in der Mitte und da bei einem Viertel in der Mitte, also bei einem Viertel und bei 3/4 der Seite, denn da schwingt die Seite auch. Und weil ich diese Hauptschwingung jetzt nicht schwingen lasse, hört man die anderen. In Wirklichkeit schwingt die Seite in allen möglichen Schwingungen. Ja, und man kann, wenn ich quasi, und da ist eben ein Schwingungsknoten bei den anderen Schwingungen, also bei dieser ersten Oberschwingung, wenn ich da den Finger so drauflege, dann habe ich eben nur die Oberschwingungen. Das kann ich dann auf anderen Bünden kann ich ganz verschiedene so Oberschwingungen klingen lassen und alle anderen dämpfe ich ab, weil da bin ich mit dem Finger auf den Schwingungsbäuchen drauf. Und so ähnlich wie mit der Seite ist es auch wieder ein Stern. Ein Stern dadurch, dass er doch sehr dicht ist, schwingt in allen möglichen Varianten. Es gibt ja Konvektion, also es ist so Sterne blubbern, ja. Und durch dieses Blubbern kommt es zu allen möglichen Schwingungen im Stern. Und diese Schwingungen überlagern sich alle und es gibt eben auch, so wie bei der Seite, Schwingungsknoten sind noch dazwischen, wo man nichts sieht, und Schwingungsbäuche ist da, wo es quasi auf und ab wobbelt, halt jetzt in 2 Dimensionen. Übrigens, wer sich das anschauen möchte, schaut bitte einfach bei den Shownotes, ist eine PowerPoint-Präsentation verlinkt und ist zwar auf Englisch, aber bei der PowerPoint sind ein paar Bilder drauf. Und wir schauen uns jetzt auch im Kurs diese PowerPoint gerade an, während wir aufnehmen. Da könnt ihr zu Hause ein bisschen mitschauen, was wir selber da gerade sehen. Also macht vielleicht jetzt kurz die Shownotes auf, macht euch im Link die PowerPoint auf und hört dann weiter. So, was hat die Glocke jetzt mit Sternen zu tun? Es hängt ein bisschen davon ab, was wir da für eine Glocke haben, wie die Schwingungen ausschauen. Wenn ich ein anderes Material habe, aus dem die Glocke besteht, dann werde ich ein bisschen andere Schwingungsmuster rauskriegen. Das heißt, diese Schwingungsmuster haben irgendwas damit zu tun, woraus die Glocke besteht. Und die Schwingungsmuster bei einem Stern haben ein bisschen was damit zu tun, woraus die Gase vom Stern bestehen. Und auch wenn ich keine verschiedenen Materialien habe, wenn die Glocke verschieden groß ist, hat sie ja auch verschiedene Schwingungsmöglichkeiten. Ne? Eine große Glocke klingt anders wie eine kleinere Glocke. Und ich kann also auch ein bisschen was über die Größe sagen. Wenn ich eine Glocke höre, dann brauche ich die Glocke gar nicht sehen, brauche sie nicht messen, sondern an dem, was ich höre, kann ich sagen, wie groß die Glocke ungefähr sein wird. Ob es eine große Glocke ist, weil es ein tiefer Ton ist, oder Bim, eine kleine Glocke sein wird, weil der Ton hoch ist. Und so ungefähr kann ich aus den Frequenzen, die ich von einem Stern kriege, ein bisschen ableiten, wie groß vermutlich eben der Durchmesser vom Stern ist. Jetzt Schwingungen und Wellen zu verwenden, um zu verstehen, wie ein Körper aufgebaut ist jetzt nichts so Ungewöhnliches. Bei der Erde müssen wir das nämlich auch machen, oder beziehungsweise ist die einzige Art und Weise herauszufinden, wie die Erde im Inneren ausschaut, ist zu schauen, wie sich Erdbebenwellen im Inneren der Erde ausbreiten. Erdbeben sind zwar schlecht für die Leute, die gerade irgendwo mittendrin sind und deren Haus zusammenfällt oder wo daneben ein Vulkan ausbricht oder was dann auch alles passieren kann, Tsunamis, die Küsten verwüsten, aber für die Geophysiker sind Erdbeben super, denn Erdbeben bedeutet, dass eben Wellen durch den ganzen Erdkörper durchlaufen und es ist so ein bisschen die Röntgenapparatmethode für die Erde. Diese durchlaufenden Wellen, das geht also durch die Erde durch, so wie Röntgenstrahlen durch unseren Körper durchgehen und aufgrund dessen, wie die durchkommen oder nicht durchkommen, kann man was darüber sagen, wie die Erde aufgebaut ist. Und da gibt es 2 verschiedene Sorten von Wellen. Und je nachdem, wo diese Sorte gerade durchgeht oder nicht gut durchgeht, sagt uns das was über den Aufbau der Erde aus.
Es gibt einmal die P-Wellen, die durch alles durch können, und einmal die S-Wellen, die nur durch Festkörper durch können. Damit konnte man auch herausfinden, dass unsere Erde einen flüssigen Erdkern hat.
Wie hat man das feststellen können?
Auf der gegenüberliegenden Seite von Erdbeben sind halt nicht mehr die S-Wellen angekommen.
Ja, sondern nur mehr die P-Wellen. Die P-Wellen, die nennt man auch longitudinale Wellen. Das ist so dichter, dünner, dichter, dünner, dichter, dünner. Das ist auch so wie Schallwellen sind. Das ist auch die Luft so zusammengepresst, lockerer. Das geht durch alles durch. Die findet man eben dann überall. Wenn es so ein Erdbeben gibt, kommen die P-Wellen überall hin. Und dann gibt es eben auch die S-Wellen, das sind eben diese Transversalwellen. Das ist so, wie wenn man so ein Seil spannt und dann mit dem Seil so auf und ab Bewegungen macht, dass sich eben solche Seilwellen bilden. Das sind transversale Wellen und die gehen gut durch einen Festkörper durch. So schwingt zum Beispiel die Saite einer Gitarre, die schwingt auch so in Transversalwellen. Aber das würde nicht durch eine Flüssigkeit durchgehen. Also ich kann durch eine Flüssigkeit keine Transversalwellen durchschicken, die verhungern da drin in der Flüssigkeit. Und weil man eben solche Transversalwellen, diese S-Wellen, gegenüber von einem Erdbeben nicht messen kann, bedeutet das, im Inneren der Erde muss es flüssig sein. Wir müssen einen flüssigen Erdkern haben. Das war sozusagen der Nachweis für das, was man sich ohnehin gedacht hat, wenn man ja schon angenommen hat, aufgrund der heißen Temperaturen im Inneren der Erde müsste er nicht flüssig sein. Und das war dann echt ein Nachweis dafür. Erdbeben sind also quasi unsere Durchleuchtmethode für die Erde. Ja, und diese Seismologie, so heißt diese Wissenschaft, dass man eben diese Beben verwendet, um das Innere von einem Körper zu erforschen, von einem Himmelskörper, das können wir jetzt auch bei Sternen machen. Auch Sterne haben Beben, jetzt nicht so wie Erdbeben, Sterne haben keine Plattentektonik oder so, das ist ja nur Gas, aber Sterne blubbern wie ein Topf heißes Wasser, werden von unten geheizt, wie ein Topf heißes Wasser von unten geheizt wird vom Erd. Ja, also im Inneren haben wir ja diese Kernfusion. Wir haben dann eine Strahlungszone, Radiative Zone steht da auf unserer Folie bei der PowerPoint. Und wir haben außen eine konvektive Zone. Konvektiv heißt, da blubbert der Stern. Heißes Gas steigt nach oben, nicht ganz so heiß, es sinkt ab. Und das führt zu allen möglichen Schwingungsanregungen. Der ganze Stern zittert also. Man könnte sagen, es ist ein wahnsinniger Lärm. Also der Stern ist laut, nur der Schall kann nicht weg vom Stern, ne? Weil der Schall kann sich nicht durchs Vakuum ausbreiten. Aber der Stern wobbelt dadurch auf verschiedenste Art und Weise. Und durch dieses Wobbeln haben wir eben dieses Muster wie bei einer Glocke. So Teile eben, die rot verschoben sind, Teile, die blau verschoben sind, die zu uns herkommen, die wegkommen. Wie jetzt ganz genau diese Schwingungen entstehen, weiß man immer noch nicht. Das ist immer noch Gegenstand der Forschung. Aber wir haben auch verschiedene Moden, verschiedene Schwingungstypen. Ja, da gibt es P-Wellen und G-Wellen. Und auch die Struktur, alle möglichen Strukturen auf der Sonne haben einen gewissen Einfluss, wie das Ganze funktioniert. Wir haben immer wieder so Instabilitätszonen, die dann bestimmte Schwingungsmuster nach sich ziehen. Aber da gibt es noch ganz viel auch, was wir nicht wissen, wie das funktioniert. Womit misst man solche Schwingungen von einem Stern eigentlich am besten? Und da gibt es einen Kandidaten, oder da gibt es Kandidaten, auf die man nicht automatisch so schnell kommen würde, nämlich Weltraumteleskope sowie das Kepler Space Teleskop oder das Cheops oder als zukünftige Mission Plato, das gerade in der Planung ist, die sind prädestiniert, die sind dazu optimal ausgerüstet, um solche Sternschwingungen, solche Sternbeben zu messen. So, Kepler, die Kepler-Mission, die kennen wir aber für was anderes, denn es taucht praktisch in den Medien oder wenn man Nachrichten sieht oder wenn man irgendwas davon hört oder liest, das immer in ganz anderen Zusammenhängen auf.
Die Kepler-Mission ist dafür bekannt, dass sie tausende Exoplaneten gefunden haben und dass es die intensivste Exoplanetensuchmaschine ist, die es gibt.
Ja, oder gegeben hat, weil die Kepler-Mission ist vorbei. Leider Gottes sind ein paar dieser Traktionsräder, mit denen man das Kepler-Teleskop einrichten kann, nicht mehr funktionsfähig. Aber ja, das war unsere Planetensuchmaschine, genau. Das war eigentlich über die Transitmethode, also dieses Vorbeiwandern von Planeten vor dem Stern, Exoplanetensysteme finden. Kaum jemand weiß, dass gerade diese Weltraumteleskope, die so gut diese Transits messen können und darum auch diese Sterne sehr genau beobachten, automatisch auch Daten produzieren, wo man diese Schwingungen drauf hat. Weil sie müssen immer auf die Sterne draufschauen, permanent, ob es da nicht einen Transit gibt. Und ein Gerät nimmt dabei auch die Frequenzen und wie genau die sich ändern, also diese genaue Struktur an Rotverschiebung, Blauverschiebung sehr gut auf. Und das gilt eben auch für die zukünftigen Missionen der Exoplanetensuche, dass die wahnsinnig viele Daten abwerfen für die Asteroseismologie. Das Ding heißt wirklich so, Sterne, Seismologie, Untersuchung von Beben, also die Wissenschaft der Sternbeben. Man kann diese Daten jetzt auf verschiedene Arten auswerten. Die meisten würden auf die Idee kommen, ja gut, schauen wir, wo wir die Rot- und wo die Blauverschiebungen haben, was haben wir für Muster. Es gibt aber noch eine andere Art der Auswertung, auf die dann eher die Asteroseismologen kommen. Die tragen auf der X-Achse ein die Frequenzen. Was haben wir für Frequenzen der Grundschwingung im Stern? Und auf der Y-Achse die Intensitäten. Und da kommt man drauf, es gibt irgendwo so einen Peak an den Frequenzen, da, wo die Frequenzen eine besonders hohe Intensität haben, wo sie besonders weit nach oben hinausragen. Das ist auf dieser Folie da so dieser Hügel, dieser Gipfel. Also da haben wir eine ganz besondere Schwingfrequenz, die besonders stark auftritt. Und aus der Schwingfrequenz, wenn man das eben so auswertet, kann man jetzt ziemlich viel ableiten. Wenn man so eine Zeitrafferaufnahme macht, so ein Close-up, eine dichte Aufnahme der Sonnenoberfläche und das nur so für ein paar Minuten laufen lässt, dann sieht man, dass sich so diese kleinen Blubberzellen, die es auf der Sonne gibt, so richtig heftig bewegen. Und klein bedeutet jetzt nicht wirklich klein, sondern das sind jeweils so, 1000 Kilometer durchmessende Zellen, die man da sieht. Da, wo es heller ist, da strömt gerade heißeres Gas nach oben und diese dunklen Ränder, die man sehen kann, da strömt gerade kühleres Gas nach unten. Das ergibt lauter so kleine Körnchen, darum nennt man das auch die Granulation der Sonne. Und das ist wirklich ziemlich in Bewegung. Also auch während weniger Minuten sieht man da stärkere Änderungen und diese Bewegungen der Sonnenoberfläche, also der für uns sichtbaren Sonnenscheibe, die kann man jetzt auswerten. Und alles, was man aus den Schwingungsdaten der Sterne auswerten kann und auch die ganze Schlusssequenz samt Verabschiedung und Informationen, die ich mit meinen Schülerinnen und Schülern aufgenommen habe, habe ich leider genau mit falscher Mikroeinstellung aufgenommen und stattdessen mein Geplaudere mit meinen Astrokurs-Teilnehmerinnen zwischendurch aufgenommen. Darum wundert euch nicht, jetzt gibt es ein bisschen schlechtere Audioqualität, dafür bekommt ihr jetzt ein bisschen Hintergrundeinblicke in das, was wir eigentlich zwischen den Aufnahmen so plaudern, denn genau das habe ich im Endeffekt in Wirklichkeit aufgenommen.
Also, man findet da die Frequenz, wo ich quasi meine wichtigste Schwingungsamplitude habe. Irgendwo habe ich da so einen Berg. Wenn ich mir alle Schwingungen so anschaue, die von dem Stern so kommen. Die kann man rausfiltern. Ja? Man braucht eine super gute Auflösung, damit ich die rauskriege aus den ganzen verschiedenen Frequenzwobbeln vom Stern. Schnelleres Wobbeln und langsameres Wobbeln und irgendwo habe ich so einen Peak. Und dieser Peak, wo die Frequenz liegt, das ist ganz, ganz eine wichtige Frequenz, aus der man jetzt einige Dinge ableiten kann. Und wenn ich das alles reinschmeiße, also die Änderung der Frequenz von diesen schwingenden Sternen, die Maximalfrequenz und die Temperatur, die ich aus anderen Messungen kriege, dann kann ich mir tatsächlich den Radius vom Stern ausrechnen. Das gibt einen Zusammenhang, wo ich dann rauskriege, wie groß ist der Stern. Und mit einer bisschen anderen Formel, wo auch nur, wie stark ändert sich die Frequenz bei dem Stern, wo ist die Maximalfrequenz und wo ist meine Effektivtemperatur, um ein bisschen anders gerechnet, andere Hochzahlen, kriege ich raus, welche Masse hat der Stern. Wie viel Kilo hat er? Nur aus den Schwingungen vom Stern kriege ich seinen Radius und seine Masse raus. Also wie groß ist er und was wiegt er? Ohne dass ich irgendwelche anderen Messungen mache. Und das ist eine Art, das zu messen, das habe ich vorher noch nie gehört gehabt. Ich finde es unglaublich geil, dass das geht. Nur aus den Schwingungen von einem Stern rausmessen, wie groß ist er und was wiegt er. Also ich höre einen Stern zu und weiß, wie groß ist er und was wiegt er.
Wie kommt man eigentlich überhaupt auf so ein Thema? Man muss sich das mal überlegen. Also tut mir leid, aber wenn man richtig Astronom ist, dann ist man in einer ganz anderen Welt. Wenn man kommt,
wie klingt ein Stern? Auf die Idee muss da mal kommen. Ja.
Oder zum Beispiel, es gibt, was auch der aus Ungarn gemacht hat, der eine ja mit der Musik im Weltraum, das hat auch einer aus Estland gemacht. Da muss man ja erstmal drauf kommen.
Ja.
Das ist...
Aber das Schräge ist, man kann damit was anfangen.
Wow.
Music of the Spheres oder so, gell? Der Silas war ja beim Treffen. Dass man mit solchen schrägen Ideen dann auch wirklich was Sinnvolles machen kann. Das ist eigentlich das Überraschendste überhaupt. Ja?
Und mit diesem Blick hinter unsere Kulissen endet unsere heutige Aufnahme. Wie immer also, danke fürs Zuhören und wenn ihr noch Fragen habt, schreibt uns auf den Social Medias oder auf keplersternwarte@gmail.com. Alle weiteren Infos und Kontaktmöglichkeiten findet ihr in unseren Shownotes. Bis zum nächsten Mal bei Astronomie am Kepler. Aber Moment, falls ihr euch jetzt wundert, warum die Folge jetzt schon aus, aber so lange ist, ich habe ein ganz besonderes Special. Desmond Grossmann hat ja diesen Vortrag beim KTD gehalten und zwar auf Englisch und wir haben diesen Vortrag mitgeschnitten und ihr könnt jetzt den ganzen Mitschnitt in voller Länge am Ende dieser Folge auch anhören, wenn ihr wollt. Und ich würde aber da empfehlen, dazu auch vorher die PowerPoint aufzumachen, die ihr für den Vortrag verwendet habt, damit ihr dort bei den Bildern auch ein bisschen mitschauen könnt, um besser zu verstehen, wovon Desmond da redet. Also, ich wünsche euch viel Vergnügen dabei.
Good, so I will start. As mentioned, I'm a doctoral student at the Instituto de Astrofísica de Canarias in Tenerife, and I'm currently doing my PhD thesis in studying asteroseismologies and unlocking the stellar secrets using asteroseismology. So we will do a deep dive for around 40 minutes. To get it, I'll just switch off my phone that really nobody can disturb me. And we are good to start. So my title says I'm using asteroseismology to unlock stellar secrets. You might now ask, what the hell is that? And that's a completely valid question because I didn't know it either until I was at the end of my bachelor course. So I will just go for the structure of my talk. So first we will discuss what is asteroseismology, what can we imagine from it. Then we will discuss how it can be observed. Spoiler, it's with telescopes. And then I'll actually go a little bit into the research I'm doing myself, into the age determination of the stars. And then we'll have a glimpse outlook in what's next, what the future is to come. So let's start right now. What is asteroseismology? Asteroseismology comes from the Greek word where astero means star or stars, and seismology means the study. This was not me.
No, this was very kind from Bar.
So what is asteroseismology? It comes from the term stars and studying of waves. So it has something to do with waves. But let's take a step back. We all know what a bell looks like. A bell usually rings on Sunday or at Mittagszeit, and through ringing a bell, through like hammering it, either automatically or by hand, you will have acoustic waves, sound waves. Those waves propagate in patterns through, in this case, the bell, and they are excited externally, which just means the bell itself does nothing, but if you hit it, it starts to ring. And you might know it if you have bells of different sizes or of different materials, the sound pattern is different. The bigger bells, they sound more The smaller bells are more like ding, ding, even if it's the same material. And if the material changes, you have got another pattern. And that's actually the foundation for seismology. So seismology you might have heard of, because we are doing it on Earth for several decades, even centuries, depends on how you define it. And it is simply the study of seismic oscillations, of seismic waves. Mostly they are caused by earthquakes. You know, earthquakes are caused when two tectonic plates rip together, and then you get a shaking, you get a vibration. That could be bad for people living close to the earthquake, but it also can be great for science. Because you see here a graph of an earthquake somewhere. This is weirdly on the North Pole, but this is just an illustration. And those seismic waves that you maybe feel, and maybe some of you have already felt an earthquake when shaking the ground, they propagate not only close to the center of the earthquake, the so-called epicenter, but they travel through the whole Earth. So they go to all sides of the Earth. And this was noticed, for example, when the big earthquake hit Fukushima. I actually was in the last grade in Achte Klasse in Kepler when this happened, and we were giving a talk on it. We could measure those earthquake waves from Japan in Austria many, many times and over 10,000 kilometers away, because those waves propagate through the Earth. But basically, it's just shifting the material. That's what's causing a wave. We measure it with seismometers. They are all around the world, and basically measure how much the Earth is shaking. And actually, this is basically the only way to study the deep interior of the Earth. You can see here, in this illustration, the Earth's the waves move differently. Maybe you know the Earth has like a crust, that's where we sit on and where we do everything. Then it has a mantle, an outer mantle and an inner mantle, and then it has a core in the middle. And the core is thought to be an iron core, and the mantle itself is liquid. It's basically like magma. And depending on the material, those waves differentiate. They move differently through those materials, and that's how we actually learned how the Earth is in the interior, because nobody was in the interior. We have been to the moon, we have sent probes to Mars, to Venus, to Saturn, to Pluto, but nobody ever has been deeper into the Earth than 20 kilometers, I think, which is on this tiny crust up there, but not much further. Yeah, so this is the foundation. That's what people do on Earth. But that's not me. I have studied the wrong thing. I have studied astrophysics and not geophysics. I have taken the wrong path, some might say. No, I'm just joking. So we can take this knowledge, what we know from Earth since 100 years, 200 years, and apply it to stars. So seismology in stars, called asteroseismology, just a fancy Greek term for it, is the study of seismic oscillations, the same as in Earth, but just not in Earth, but in a star. But the question is, what is it caused by? There's no crust, no Earth crust tectonic plates on the star that can cause an earthquake. And the second question is, how can we measure it? I mean, we don't have a seismometer on the star because it will probably burn immediately. So those are two of the questions I try to answer in the talk today. And a spoiler, seismology is actually the only proper way to study what is inside of a star, similar to the Earth. With a small exception, some of you might have heard of neutrinos. They also can get us information, but I will just ignore them for the moment, excuse to any neutrino scientists. Apart from that, seismology is the only way we can look in the depth of the star. So that's the foundation. I spent a little bit longer on those slides because it's very important to understand those concepts. And now we will get a little bit of a dive into it. So how do those oscillations on a star arise? We said on the Earth, they came from earthquakes, from tectonic plates on the surface hitting each other and causing rattling. But now we have a star, which is somehow similar, but in other ways very, very different. And I always like to imagine a star as a pot of boiling water. It's heated from below because the energy is created from the bottom in the core, and the heat wants to get up, and that's exactly what you do when you put a pot of water on an oven. You have heat below, and the heat rises up, and you'll have boiling water with a lot of bubbles and a lot of action going on into it. And I would not recommending you touching it. So the problem is now, okay, we have the heat, the energy, the heat is created in the core of the star. I won't go into too much detail, but it's done through what we call nuclear fission. Basically, it's a hydrogen atom to Wasserstoffatome getting together and in some process building helium. And by this process, nuclear fusion, not fission, fusion. Nuclear fusion, by this process we can create energy. It's a whole other topic, and you can write books and books about this topic alone, but it's just important that we have energy coming from the core and wanting out. This energy is in the form of heat. So the core of the sun has about 15 million degrees of Celsius. So it's unimaginably hot, much hotter than anything we've ever seen. But this energy, this heat needs to get outwards. So how is this heat transport happening? There are basically three different mechanisms for heat transport. The first is what we know from day-to-day life. It's radiation, Strahlung in German. Basically, if you lie down in the sun will hit you. The light from the sun will hit you, and you will probably feel hot after some time, just as I had it after lunch right here. That is radiation. Okay, this is what we know. It's getting hot. And Strahlung is coming outwards and transporting the heat from point A to point B. Then we have something called conduction. It's in German Wärmeleitung. So basically, if you have two metals together, zwei Metalle, and one of them is hot and the other is cold, the other one will get very hot as well, very, very fast, because the heat is going through the material. Wärmeleitung, conduction. Those two are not of great interest for today because they are very inefficient. They are not really good in transporting heat. Sometimes they're the only possibility, but in a star, they are not really usable. They happen, but only very, very rare. The most important one is what we call convection, convection. Maybe you have experienced that when you have in the winter heated up your apartment and you open the window, you will suddenly get like a flow of air through the whole room. And that's basically convection. When material, the heated material from your Heizung is moving upwards towards the colder area, that would be convection. And this will become important very, very shortly. So how do oscillations arise now? I told you now so much about heat transport, but why is this important? Because a star is actually a ball of gas. It's basically nothing else. In the middle, it's more dense. In the outer sphere, it's less dense. But apart from that, it's not really special in any other way. However, in the star is not completely stable. It's not like a ball of whatever sitting there and doing nothing. Since energy is transported in the interior and wants to get out, it's like this boiling pot of water, where a lot of things are happening, a lot of what we call instabilities. Things are moving, things are going on, because the heat wants to go out, the gravitation wants to push in, so they are fighting against each other, basically. And that's where the oscillations come in. So this is the wrong picture now. I wanted to show a different one, but yeah. What most people in the field are dealing with are so-called solar-like oscillation. Spoiler, they are called like this because they were discovered first in the sun. Those are made by convection, by this movement from the bottom to the top of the star, from the inner to the outer surface of the star. If material is moving, and basically moving material in a certain pattern is nothing else than an oscillation, a wave. That's what you experience, for example, if you are on the beach, you experience waves coming in. And the waves are just water that was moved by probably the wind or by some ocean current, but it's just moving material. Those solar-like oscillations are what we call occur in stars like our sun. So the sun is in the so-called main sequence, basically just termed because we found most stars there, and in red giants. Red giants are marked here because I'm researching on red giants. And actually, we have found those oscillations in stars in over 100,000 stars in the sky. Up to today, the number might even be higher. It's what I found from 2020 at the moment. Just go back here to the graph. Can you see my mouse? Yeah. So you see here basically like a slice cut out of the sun. And you see here basically an artist, what an artist thinks of oscillations. They are basically waves going from the surface to the surface. They are bouncing back, they're getting reflected, going back in, getting reflected here, going back there, reflected, and basically this goes on for some time, not forever, but for some time. That's one sort, and but the other sort I will discuss in a second, but that's basically how the waves go through, propagate, move through the star. Very, very similar to what we have seen before and what we know from the Earth. So this is just an explanation. So what I've shown you, there are two different kinds of waves. They're called pressure waves and gravity waves, P and G. So the pressure waves, they are like sound. Sound is nothing else than the air around moving and getting to your ears. And they bounce back at the surface of the star, and they are mostly close to the surface. And they are called pressure waves because they are caused by the pressure that this convection gives the material. Then we have something called gravity waves. They are basically more like the beach waves. They only exist in the interior of the star, as you can see on the right-hand side here. So the left-hand side is the pressure, the right-hand side is the gravity. And you see it's a beautiful pattern of a rose. And it's comparative to what I told before, to the waves on the beach. They are done by the wind, and they hit you, or they hit the sandy beach. That's what we would call gravity waves, because basically they are killed or killed off by gravity at the end. Because when the wave hits the beach, and then the wave is gone. The wave doesn't come anymore. That's the two different. It's not that important. This is just an extension of what I've been talking about. So this is a brief spoiler. I was talking about the solar-like oscillations. Stars oscillate that are familiar as our sun. But many, many, many more stars oscillate. Many, many more stars have waves in them. Some examples include Cepheids, Arlyre stars, which are also variable Sterne, white dwarfs, weiße Zwerge, many, many more. For the interested viewer, you see here on the right-hand side Hertzsprung-Russell diagram, so basically temperature and luminosity of a star. And you see the many, many other types that can cause oscillations. Actually, I am just working on this small spot here, the blue one. This would be the sun, the position of the sun. And the red giants are up there. So those are the solar-like oscillators. Here we have the Cepheiden, which are very important for distant measurements. And then we have many, many other more. Down here, the white dwarfs, Myra variables, Delta Scuti. Even I don't know what many of them are doing. But people are working on it, and they all oscillate in one or the other way. But I'm focusing here on the solar-like oscillations, because they are, let's say, the easiest to detect and the most important one, because we know them from the sun. So speaking about knowing, how do we observe them? How do we actually know that this thing is oscillating? I told you before, on the Earth, we have a seismometer put on the ground, and it measures when the ground is shaking. But we can't put anything on a star. That would be crazy. But we have a solution for it. And I have now brought you a beautiful, beautiful video. This is actually a video from the biggest solar telescope in the world, called Dicklist in Hawaii. And this video is provided by the National Science Foundation. And you can see a basically extreme zoom in to the surface of the sun here. I hope you will see the video playing in a moment. And you see how this is actually moving. This is not in real time. You see the time moving on the bottom right. But this is only about several minutes. So this is in a scale you actually can watch. Play it again. And you see in this picture, there are parts that seem bright, and there are some parts that seem dark. And actually, this is exactly what's happening on the surface of the sun. We have material that is moving towards us, that seems brighter, and material like on the boiling pot, and material moving downwards, which seems not so bright, which is the dark edges here. So basically the sun, this is basically a picture of the sun as a boiling pot, nothing else. And you can imagine those bubbles as the bubbles when you boil water. So still I haven't given you the answer on how we measure those kinds of things. Basically, there are two ways. One way is called spectroscopy. So it is spectroscopy. So basically, what it does is it looks at those moving parts, and it detects the movement of each of several of those small bubbles. Let's call it like that. And it does it by using the Doppler effect, where like parts that are moving towards us are shifted in the wavelength, and the parts that are moving away from us are also shifted. That's like the classical effect when an ambulance car is moving towards you, it sounds different when it moves away from you. The same effect, excuse me. So those movements were discovered on the sun in the 60s, in the 1960s. Actually, they were discovered mostly here on Tenerife, where I sit at the moment at the Instituto Astrofísica, with the telescopes on the mountain on Teide. And it took several years, 30 years, to discover them on other stars as well. Those measurements are mostly done by telescopes on Earth, like the ones on Teide or like the ones in Hawaii. And they require very, very good resolution. So you need a very big telescope with a very sensitive instrument to observe them. So this is the one way you can do it. And the other way, that's the one way you can do it. And I have even prepared a picture, I've forgotten. Basically, when you do this on the sun looks more like an egg at the moment here to me. You can observe something very, very nicely. This is a diagram where basically the darker edges are moving away from us, and the more bright ones are moving towards us. So what we see here is basically the rotation of the sun, because the one side is moving away from us, while the other side is moving towards us. And you see in the middle all those like speckled dots of bright and dark and bright and dark. And this is exactly what I've shown you before in detail, what you can see here. This is just the extreme zoom in of basically this picture. Yes, that is one method of how we can observe it. The other way how we can listen to a star is the classical way, some might say, what we call space photometry. What is photometry? Photometry is nothing else than taking a photo of what you see with your telescope in a more cool way and a more sophisticated way. But basically, it's what you do with small and big telescopes. When you do not look into them, you usually have a camera, take a photo. This is photometry. So what does it do? It actually takes photos, but mostly it is there to measure the brightness of a star. How bright is it? So how much light is coming from the star? And it can basically measure that over time. When we do this, the best possibility is to shoot our telescope in space. It might be a little bit expensive, but it is still the best because we do not have any atmosphere, any rain, any clouds, anything that could annoy us. And we shoot the telescopes into space for this. So again, we need a high sensitivity, and we also need long time scales. On the right-hand side, you see here a graph by a colleague of mine, which basically you see on this side the time in days, and you already see it's over 1,400 days. So the smart ones of you will have calculated already that this is around 3 to 4 years. So this is a very, very long, and this telescope took every half an hour a measurement, saved it, and sent it back to Earth. And this is basically the end result of this whole 4 years of observations. And that's actually be very important in the next slide. I think it's the next. So this, what I've shown you, comes actually from the Kepler Space Telescope. You might have heard it, and I mean, you surely know who Johannes Kepler was. And actually, when I was in the Kepler Gymnasium, I did my final vorwissenschaftliche Arbeit on the Kepler Space Telescope. It was started in 2009 and basically was made to observe exoplanets, something completely different. I have nothing to do with exoplanets in that sense, but it is very, very important nevertheless. So it is usually just watching over 100,000 stars at the same time and measuring the brightness every 30 minutes, every half an hour. And it did this for over 4, almost 5 years. until it was unfortunately a little bit broken and it couldn't work the way as it was intended. So usually you might have seen this sometime. You have this transit where the exoplanet is moving in front of the star, and you get this dip in brightness, so it's getting a little bit darker, and that's why we know we found an exoplanet. So that was actually the main idea of Kepler, finding exoplanets. And I didn't know, when I was writing my thesis in high school, I didn't know that actually Kepler was used for something completely different as well. Namely, it was used for asteroseismology. I've only learned that at university, and I was very surprised because nobody's talking about it, because only the exoplanets are cool and nothing else is. It is very, very important for asteroseismology. And I will explain you now why this is. So maybe this is the right point to ask if everything at the moment was understandable. Questions we can have at the end, but if there's anything that's completely off, please let me know. Yeah. So asteroseismology with Kepler. So I've talked the last few minutes about how Kepler is measuring the brightness of stars, and you might now ask me, why does this matter? Because actually, you see here a light curve actually from my bachelor arbeit back then in 2017 from the Kepler Space Telescope. Again, just time over brightness, nothing else. You see some nice features here. They are not really important. They're called heartbeat events. They're related to how the stars interact, but that's not the point of this. So this is how we usually look, how most people, even most scientists, look at it. The time versus the brightness. And then we look, oh, is there a variation in brightness? Did we just find an exoplanet? Did we find some activity of the star? Whatever. That's what we call a light curve. And I think 80% of scientists working with Kepler data or with any space telescope data, they're just looking at this. They're not caring about anything else. But I'm different. We are different. We are actually looking at something that is called the frequency domain. And it's getting a little bit difficult. It also took me time to understand it. So completely fine if you cannot look through all of it. But I try to break it down. So at the moment, we're looking at time versus brightness. But we can change that. You probably have heard about the term frequency. Every wave has a frequency, the light has a frequency, the sound has a frequency, measured in hertz usually. And actually, we can translate it. We can go from the time that we have measured, and we see some repetitive patterns here, some Wiederholungsformen. And we want to know how often do they come, in what frequency they occur, in welcher Frequenz. And actually, there is a lot of mathematics involved. Even I don't understand every part of it. For the more advanced of you, it is called Fourier transformation or fast Fourier transformation. And this basically gives the same. So this and this are basically the same. Just that here we have now the frequency, and here we have something we call power density. Technically, you can say it's an amplitude, it's an amplitude. Doesn't really matter. It's not really important. It just needs to be clear that it is a kind of amplitude. And that is what we call an power spectrum. And with this, you already see some lines. I have put those lines in my bachelor thesis in there, and I'm doing the similar thing in my master thesis and in my doctor arbeit. And you can see some bump here, and I will explain this shortly. But this is the instrument we are working on. We are taking the data from Kepler, for example, which is just measuring brightness, taking photos, nothing else, and we switch it to frequency. That's all we do. There's a lot of things more evolved, but in general, that's what we do. So now you might ask, what the hell is he talking about? Why is this important? And you saw this, let's call it like a cone, this peak, like a mountain. And this mountain is called the power excess, which basically just means the frequency is more powerful. The waves are more powerful in this area. I've marked this here with a red marker. In case you wondered, the gray and the black ones, the black one is just a better version of the gray one with some fancy mathematics involved. I don't even know how it's properly done. I just worked with it. But just look at the black one. And you see this peak here. And the peak of this mountain is what we call the frequency of maximum oscillation. I mean, makes sense because it's where these oscillations are most powerful. The amplitude is am höchsten, is the highest. And that's what we call frequency of maximum oscillation. Now, why is this interesting? It's interesting because it's actually helping us to understand the star. The mathematical equation relation you do not really have to understand. I just took this slide from one of my other talks. The important thing is this nu max, what we call it, nu is just the Greek letter, this frequency, is related to mass, the temperature, the radius of the star. And we can even get something more detailed. So, slide here. If we zoom into this mountain, this is this mountain, just as a zoom in version, you see clearly a pattern like a cone. You can make your hair with it. I'm just joking. And the distance between those oscillations, every peak is an oscillation, is what we call delta nu, large frequency separation. The names are very uncreative and you don't have to remember them. It's just important what they tell us. This parameter is very important because it is related to the speed of sound, to the Schallgeschwindigkeit in a star. And this Schallgeschwindigkeit in the air, it's about 330 meters per second, if I remember correctly. And it differs. You maybe know that if you go into water, sound is moving faster. If you go into steel, it's even moving more faster than this. So this delta nu tells us what is the speed of sound into the star, because those waves are basically sound. And that's amazing because it tells us what is the star made of? How big is it? So it has a correlation with mass and the radius of a star, which is amazing. Oh, why is this happening again? And this, I promise you, this is the only really equation I'm gonna go into. There won't be any equations anymore. And with some magic relations, our knowledge of the sun, we can basically get the radius and the mass of a star by only knowing these two parameters, the delta nu, the separation, the distance, and the nu max, where it's like the peak of this pattern. Plus, we need the information about the temperature. We can get that from other measurements. That's not that difficult. And if we just put that into the equation and compare it to the values down here, which are basically everything with a symbol, with this dot is the solar, the value of the sun, for the sun, for the sun, for the sun. And we know this one very, very well. We get out the mass and the radius of a star. Without knowing anything else about it, we can know the mass and the radius of the star. And this is amazing. And this is a summary slide. In the meantime, I have some more slides, but this is the most important takeaway. What can we learn from seismology? We can learn how heavy a star is, what mass it has, what radius the star is, and we can learn about the chemical composition, die chemische Zusammensetzung. So stars are mostly made of Wasserstoff, of hydrogen, we call it X, then of helium, we call it Y, and everything else, what is not Wasserstoff or helium, we call metals in astrophysics. Please don't tell that to your chemistry teacher. They will probably make a problem with me. But we call them metals. Carbon, oxygen, iron, everything else. And from this seismology, we can get a picture of all of those things. So that is the general part on asteroseismology, and 2 or 3 slides. I just want to tell you what I am doing the research about with asteroseismology. And I actually care about the age. I actually want to know how old are stars. And actually, age is very, very difficult. Because age, oh, there's an error in my slide, sorry. We can observe the radius, the composition, the mass. Age should not be there. But we cannot observe the age. The star doesn't tell us how old he is. I mean, it's when you see a human, you might know, okay, he's rather 60, 70, 80, or maybe 10, 20, 30. But can you really tell apart between the 40-year-old and the 50-year-old person? I cannot most of the times. It's very difficult. And it's the same with stars. And actually, that's what I'm interested in, because at the moment, the error, the failure that we have in the measurements of the stars is huge. This is basically a graph on the measurements of the age and the age, and it's going crazy. It gives us 30, 50, 100% errors. So it would be basically, you see a person, you say he is 40 years old, plus or minus 40 years, which is completely useless because nobody can get anything from it. So we need better models, more constraints to get a higher precision in age. And actually, that is one main takeaway from this talk. The mass of the star is very important. If a star has little mass, very light, the stars can get very old. And I talk of the age of the universe, 13, 15, 20 billion of years. If a star is very, very massive, let's say 20, 30 times the mass of the sun, it only lasts for a few million years, which is long for us, but for the universe, it's yesterday. Why is that actually? This is because if a star has more mass, it puts more pressure to the core, to the middle, to the interior of the star. And if this core gets more pressure, it's working harder. Like when you have a deadline for a house room, you're working harder if the deadline is close. It's basically how the star does it. And so it's going faster and faster and faster, but there is only so much fuel, mostly hydrogen, in a star. So this is used much, much more. So basically it's comparative to when you drive a car at 200 kilometers per hour, you will have much less of what you have put into your benzene than if you drive 50 kilometers an hour and get a nice ride. So the nice thing is, as I told you before, from the asteroseismology, we can get a very accurate mass estimation. And from this mass, we can get a very good age, actually, because it's this factor that does age very, very well. And yeah, on the left-hand side, it's basically part of my work. I'm investigating two stars in a binary, Doppelsternsystem. Mass for the first one is on this axis, mass for the second one on this. And basically the best solution I have found is this triangle, this Dreieck, and it perfectly fits where it is supposed to be. So that basically shows what I'm doing. I'm doing hundreds of thousands, millions of models and basically compare it to what we observe. This is, just the other part of it. With this, I have done 1 million models of a star on a computer. And basically, I'm comparing the parameters of the model, temperature, mass, radius, with the observations, temperature. And what I told you before, these frequencies we know, which relate to mass and radius, we can observe. And then I can see, okay, at which point is the best fitting model? And here you can see it is located around 2 giga-years is just a fancy term for billion years, Milliarde, 2 Milliarden Jahre, which is not too young and not too old, so it's intermediate. Would be, for humans, it would be like 30, 40 years old, I would say. So with asteroseismology, we can actually get a very, very good age determination and get better age than with any other tool before. So I'm already coming to the end part of my talk. So what's more? And this is now getting a little bit advanced, but this is on purpose. If you're curious, you can study those things. So what has asteroseismology to do with quantum mechanics? So I just told you before, we have those oscillations, and they're basically all similar. We have these P, pressure waves, the gravity, but apart from that, all the same. Yeah, that's not true. Not all oscillations are the same. Actually, a star we consider as a perfect sphere, eine perfekte Kugel, which it is not, I know, but we still do it because we simplify things. And maybe some of you have heard in quantum mechanics, people use these Quantenzahlen, quantum numbers, NLM. And we also use that in asteroseismology, basically to tell at which point the notes, the Knoten of the Schwingung, you might have heard that in music class, where you have this vibration and then you have a knot, and the vibration is going on, and there's another knot, to basically tell where those knots are located. So basically, stars are described like atoms, kind of. This is very advanced. It even took me as a late bachelor student to understand quite a time. But nevertheless, it's very interesting, and I wanted to show it to you as well. So I mentioned the Kepler mission. Kepler mission was really cool for exoplanets, but also for studying stars, for asteroseismology. You might have heard of the TESS mission, which is basically the Nachfolger of the Kepler mission. It observes all of the sky, but for a shorter wavelength. You see the logo here. And in a few years, we will have the Plato mission by the ESA, which is not a philosopher, by the way, but it's named after it. And it will also study exoplanets and stars using seismology. And we also have observations on Earth, observational networks like the SONG. We have a SONG telescope in Tenerife. Here, I visited 2 weeks ago. We have in Hawaii, we have in Australia, we have in China, in South Africa, and they are all together observing stars and looking for their oscillations. So we will get more data, which is good because it enables us to do better science. And as a summary, we go back a step and say, stars oscillate, they vibrate, just like the Earth. It allows us to get a glimpse into the deep interior of the star, which isn't possible otherwise. And the oscillations, and that's the main takeaway I want you to know, they are related to the mass and the radius of a star, and very important for the age of a star. And that's why asteroseismology can do so many amazing things. Even more amazing things when we get more observations, more data, and more missions in the future. So exciting times are to come. And I want to leave you with this video where basically it shows you, demonstrates you the oscillation in a much, much exaggerated way. So it is much, much, much smaller, the movements in reality, but you can see it here visualized, the stars vibrating, oscillating in different ways. I'll just repeat the video. Vibrating and oscillating in different ways, helping us to know them even better. And that's where I say thank you very much for the talk. And I'm happy to take any questions. I hope it was made a little bit understandable.
Thanks,
I have one question, if you can hear me.
Yes.
Hello.
Yes.
I understood the relationship between the mass of the star and the lifetime of the star. So if you say it's, for example, 10% of the solar mass, and it's going to be a red dwarf, and it's going to last for billions and billions of years, many billions.
Yes.
I understand that. But what I missed is, how do you tell what is the age of this particular star right now? Is it, did it get created 1 billion years ago, or did it get created 10 billions of years ago?
So basically, as you said, the mass is already important and tells us one piece, but not everything. The second important piece is the radius, because stars usually tend to blow up, get bigger. Let's say the sun in 2 billion years will become a red giant. It will go up and up and up. And if we know this combination of the mass of the star and what radius, we can basically go back, do our modeling. That's exactly what I'm doing at the moment, and say, okay, it has this mass, and at a certain age, it's supposed to have this radius, or this radius, or this radius, or this radius. Mostly getting bigger. There are some exceptions, but in general, getting bigger. So basically, when I see the star and I know the radius and the mass, I can say very, very well at what stage, like with a kid, basically. The kid grows, and usually a kid with 1.70 meters is older than a kid with 1.10 meters. Not always working, but in general. And that's similar for stars.
Thank you, I understand.
Ja, ich hoffe, ich war halbwegs in der Zeit und nicht zu.
Eine Frage hätte ich noch. There's one question left. I would like to ask to you. Most of the stars are not alone, but are in double star systems, multiple star systems. Isn't that a thing that makes it very complicated? Do that change the oscillations?
I'm very happy that you asked the question. The answer is a clear yin. I'm working with binary stars. So what you see here, as I told, I'm working with binary. The one side is it helps us because if I have two stars, usually I can assume they are the same age. So they had to have the same time to get to the point where they are. They have the same composition, the same Zusammensetzung. So this is the part that helps us. The part that doesn't help us is if the stars are too close to each other, they influence each other quite much. And this influence can override the oscillations as well. So the perfect binary would be something like, I have it 100, 200 days, still far enough that they don't influence each other too much, but still close enough that we can see the interactions in between them.
Fine, thank you.
That leads me
You're
to
welcome.
another question. Recently,
Yes.
there was a system that was discovered that used to be a triple star system. And then it was determined that right now it's only a double star system. The third star is missing, and it was determined that it must have been there before, and it probably collided with one of those stars. So when two stars collide and you measure their seismology, how does this change the parameters of determining the mass and the radius? Does it still work or not?
In general, you have to be very, very careful. It depends. There are actually theories of where like one star has eaten the other one. And I have a colleague here in Tenerife who is working on like this mergers. And there are theories and models where you can say, since mostly if they collide, they're not exactly the same, they are different. So you can notice in the oscillation if something is wrong, let's call it like that. We haven't found such things yet, such composite objects, but we know in theory how they are supposed to look if we do the asteroseismology. And yes, in this case, this won't be as simple as I've just shown it to you anymore. This is basically the most simplification, and then it can get beliebig kompliziert. Let's call it like that.
I see. So if you're looking for such a system, there is one posting in the Google News today about it. So you can find the name there. But thank you.
Wenn wir beschließen, oder? Dankeschön, dass du dir die Zeit genommen hast.
Bitte gerne.
Den Einblick in die Forschung zu kriegen. Es war vieles ganz neu für mich. Ich bin ganz begeistert. Ich hatte nicht gewusst, dass man auch diese Massenradiusbestimmungen mit der Asteroseismologie machen kann. Ich dachte, es geht nur um die Zusammensetzung. Das ist wirklich eine ganz coole Sache. Ich glaube, wir haben viel dazugelernt. Eine tolle Forschung, die du da machst.
Es ist sehr aufregend und ich freue mich sehr darauf. Und es gibt immer wieder Neues und ich bleibe dem Kepler gerne treu. Und ich freue mich sehr, dass ich heute auch einen Vortrag geben durfte. Ich hoffe, er war verständlich.
Wenn du wieder mal da bist, dann werden wir uns einmal melden.